Cool. So I'm Jonathan. I'm a principal engineer at TransferWise. Um, and this set of slides is mostly about our sort of journey with Spire and how we are using it. I'm just getting my speaker's notes. Sorry if I'm looking away from the camera. The camera is away from the monitor at the moment. So I'll get started. Who's TransferWise? Well, TransferWise is a global technology company building the best way to move money around the world. That is pulled straight from the PR slides. Here's some random numbers about the company. I guess the most relevant one here is the number of routes that we operate in. So this is the number of FX routes that we have open, the number of countries that we operate in, and operating that number of markets, many of which we're directly regulated in, others of which we work through partner banks, comes with a very high regulatory burden. Everywhere is different. Every US state has its own regulatory own rules, for example. And we also have to integrate with a number of different payment systems. Faster payment system in the UK, for example. Each of those comes with their own rules, their own regulations, and some very strict technical requirements as well. And in terms of payment schemes, probably the one everyone's heard of, well, the set of rules that everyone's heard of is probably PCI DSS, which the payment card industry uses. Basically, think variations on that for a lot of the other rules that we have to follow. So how do we run all of our things? Well, we spent the last 2 years or so migrating out of virtual machines which were running in VMware vSphere into Kubernetes running on AWS. That's not EKS, that's our own sort of self-managed Kubernetes. We've still got data centers to meet some of the scheme and regulatory needs. There's always a need for hardware somewhere, landing connections, certain schemes require certain HSMs and that kind of thing, so they still have to go into data centers. So that gives us a mix of virtual machines running in data centers, EC2 instances, and we've had the vast majority of our workloads running in Kubernetes, in AWS and in data centers. Most of these services, kind of goes without saying, it's a microservices architecture. Most of them are written in Java, but there are some other languages around. There's some Python, there's some PHP, there's some Go, and there's probably a bunch of other languages as well running in the mix. There are various other important services. So things like we're quite a heavy Kafka user, so we have numerous Kafka clusters. We use HashiCorp Vault in various places. There are obviously various databases, various other data stores around as well, and probably a big list of things I've forgotten. We use Envoy very heavily. We've got a sort of full service mesh between all these services, and that runs using an in-house control plane. And because of a lot of the regulatory requirements and the scheme requirements, we have a lot of isolated, well, we have several isolated trust domains. So those are basically, obviously they need to be able to talk to each other, otherwise they're not much use, but services in them have to be as isolated as possible from the rest of the system. Now, services, as I said, need to talk to each other, and they need to be able to authenticate to each other and to these other components of our system. Whoops, sorry, I managed to go back to the start of my slides. So we have collected numerous ways to do this authentication over the years. Lots of shared secrets around, either deployed through Ansible Vault or kubectl sealed secrets in Kubernetes. We have AWS IAM usage around. Obviously, that's only that useful in EC2. We have Kubernetes service account tokens being used in a few places as well. But most of our service authentication uses JWT, which are issued by a centralized auth server. That has some scalability challenges with it, though it's better than when it was using OAuth between all the services. And then sort of the final option, in a few places, we have systems that just trust everyone who's within a given perimeter, which is not ideal, but there are a few bits and pieces that do that. Challenges with these approaches? Well, everyone reinvents new ways to handle secrets. Each time they do that, they tend to do it badly. Most people would consider only the happy case when they're doing something like this. So they rarely consider what happens when a secret leaks, and inevitably they do. Most commonly, they end up written out into a log file by accident, but don't put it past someone to make a really silly mistake and upload a heap dump to heap dump analysis that doesn't steal your secrets.com or something along those lines. And even if that does happen, don't expect anyone to tell you about it. So you may not find out that some of these shared secrets have leaked and that you need to rotate them. The more a secret shared, the more likely it is to leak at some point, and the more painful rotation of it's going to be. So many of these mechanisms created rotation nightmares and difficulty in knowing whether or not secrets are really secure. It's also very easy to build mechanisms that look quite clever on paper, but create tremendous scalability issues. Often not necessarily in terms of computing scalability issues, more often they create operational issues which aren't apparent until such system is starting to be used more heavily. We have challenges around trust boundaries. So we have these multiple trust domains. How do we authenticate services between them securely? Some of these mechanisms that have previously been used make it quite hard. So we were looking for a way to replace at least some of these systems. The replacement needed to integrate well with our service mesh. It needed to avoid long-lived secrets and avoid overhead on every single request as much as possible. And ideally, it had to be as low touch as possible for service owners in order to get it adopted as rapidly as possible. So we started looking around and thinking about what we'd do. We looked at building something of our own, and as we sort of were getting through the design stages of that, we found Spire, which matched quite closely what we were thinking of building anyway. And obviously with security products, it's much better to be using something that a lot of eyes have looked at. So an open source project was ideal, and it avoided us reinventing the wheel yet again. So we started deploying Spire. The main use case for it, Envoy, everyone's probably heard a lot of Envoy use cases, I would imagine, but it's our biggest user, so I guess I sort of need to mention it. All of our service calls are done via our Envoy service mesh that I mentioned earlier. Services speak plain text, HTTP1 or 2 or gRPC to their local Envoy. That upgrades to HTTP2 and MTLS to the remote services envoy, and that remote services envoy decrypts it and sends plain text to the destination service that's running locally. That destination, so the local envoy on the client side ensures that the remote SPIFFE ID matches what it expects, so we can guarantee we're speaking to the correct service. And on the remote side, the receiving envoy, when it does the decryption, adds a header containing the validated SPIFFE ID from the X509 SVID to the call to the local to the remote service. So this handles authentication for us, and it's then up to the service to take the SPIFFE ID that's been passed in the header as a principal and use that for authorization. We're currently using the Spire Agent SDS API implementation, so the Envoy secrets discovery service implementation for Envoy, and that's working quite well. Another use case that we have for it is Kafka. So we use Kafka quite heavily. We have been using the Java SPIFFE library on both the client and broker side. This obviously only works for Java. On the broker side, we then populate the Kafka principle from the X509 SVID, and that work had already been done by Triana, so we're using their Kafka module for it. And then Kafka ACLs are used based on that principle. So that's great, and it works really well for Java clients. However, we have non-Java clients who can't make use of this mechanism. And it would also be nice if we could make this transparent to even the Java clients, because we would ideally like to avoid service owners baking the Spire client library into their services. So we've got a proof of concept to use Envoy to make this transparent, which works quite well as a proof of concept, but at the moment it relies on IP tables redirect rules to basically hijack, and Envoy original destination load balancing to hijack the request of the brokers. That's not usable in our Kubernetes clusters because the easy approach to doing it would break our pod security policies. We have a few options for dealing with that, and I will share more when we have that working, I guess. But that's quite exciting. Again, this is working really well for us with Kafka. Now, I talked about multiple trust domains. How do we authenticate trust domains to each other? And this is probably the interesting bit. So we started prior to any of the talk of federated bundles and things. So we've gone down the sort of PKI-based route for this. We have an offline certificate authority that's used as the trust bundle effectively, one per environment. So there's a production one that's separate from the staging and the sort of development ones. We are very familiar with dealing with offline keys. Some of the payment schemes we work with require them. So we have procedures for offline key signing ceremonies and that kind of thing already. So we're familiar with doing that. So that was kind of easy for us to adopt. The offline CA is used to sign intermediates per trust domain and is then loaded into an AWS private certificate authority in each trust domain. Those intermediates have name constraints on them to prevent them issuing things from a different trust domain. And then SPIRE server uses the private certificate authorities as the upstream CA. So that works well for us because while the X509 spec does correctly say that some client libraries don't support name constraints correctly, we are lucky enough that we only have to work with client libraries that do. So this is working acceptably for us. We're quite happy with this as a solution. We gather audit trails from ACM PCA, so we know what that's issuing, so we can detect cases where something isn't a SPIRE server. If there's a compromise and someone starts getting hold of SPIRE server credentials and issuing certs, we can detect suspicious activity there. In theory, compromise of one SPIRE server, so getting the ACM PCA credentials, means that because of the SAN constraints, you can't issue certificates for another trust domain. So any compromise should be limited to a trust domain in terms of being able to issue arbitrary certs for services in that one trust domain. We've got procedures for rotating these and revoking them. So at the moment, the revocation for intermediates is based on CRLs, and there's an out-of-band mechanism for distributing those to the clients. In the case of a route needing to be rotated, that's going to be very painful, but we expect it to be quite rare. There is a documented procedure for that. We've mostly aimed to make things that we expect to happen more commonly, sort of more likely risks. We have as much automation and easy to follow procedures around that, less disruptive procedure around those as possible. Anything that's considered quite unlikely, we've accepted more disruptive procedures to try and deal with the offline CA being compromised being one of them. Benefits of this setup. Well, moving to SPIRE has allowed us to slowly phase out some of the older systems for authentication and also introduce security in those cases where it didn't exist, where things inside the perimeter were just trusted. This has given us one system to maintain with a very clear internal owner. And especially if we can make the Kafka usage even more transparent, it will be even more sort of clear where the boundaries of these systems lie. We've got well-tested and documented processes for operations such as rotation and handling secret compromises, which is great. And because this has got rid of pretty much all long-lived secrets, the risk of secret compromise is a lot lower as well. We still have X509 POP testers lurking around, so of course there's still key material for those, which is effectively a long-lived secret. But that isn't handled by systems outside of this team's ownership. So the X509 POP secrets, of course, are not handled by services themselves, only by the SPIRE agents, which is great. and this has been great because we didn't have to reinvent the wheel again. A lot of hard lessons didn't have to be relearned. Remaining challenges around setup. We started using SPIRE comparatively early. It's taken us a long time to get from test deployments into production because it's a very big and scary change to start turning this kind of thing on across the system, across the whole system, because it can break quite a lot. So the rollout has been very gradual and very time consuming. The problems we have left, testing non-Kubernetes nodes remains a big challenge for us. The AWS IID attesters time of first use checks are an operational problem, especially in staging development environments where the agent can remain disconnected from SPIRE server for a while. Distributing X509 POP keys is, again, a challenge around attesting non-Kubernetes nodes, but the story within Kubernetes is a lot better. For workload registration in Kubernetes, we wrote our own workload registrar using the, rather than using the existing one. That's based off custom resources. So we have a SPIFFE ID resource that gets created when a new service is deployed, and that eventually leads to SPIRE entries being created. That has had some work on it as well by Faisal from F5 Networks. But it's hit a bit of an impasse where we'd really like to upstream it, but there's a few open questions around exactly what direction it should go in. It's solved our problems very nicely, but it needs to solve other people's problems as well. There's a few other minor operational headaches still. So there's a bug where agents weren't reattested to the SVID at Spires. Again, this is mostly a problem in test and development environments, but again, it's a bit of operational overhead. Overall, though, we're very happy with the outcome, and everything seems to be going quite well. So any questions?
Great, Jonathan. Thank you so much. I think it was a fantastic presentation. Looking at the comments in the chat window, and the applaud from the audience too. I can read the questions for you. I know Matt from Square had a question. Matt, you want to unmute and just ask the question, or is that better?
Yeah, sure. So the question I had was, you mentioned earlier that Envoy is passing the SPIFFE ID to your workloads in a header. Are you using the standard Envoy X-forwarded client cert headers?
No, we're not. We're using our own header that just contains the SPIFFE ID.
Yeah, okay.
Decided to be a bit easier than these services having to parse the standard certificate header.
Right.
Okay. I know Emilian asked just a quick question. What client libraries are you using with SAN constraints? We just want to know the libraries and versions. If you can share this info right now or offline.
I don't have them off the top of my head, but I can go and grab them for you.
Okay. And Peter, do you want to unmute yourself and ask your question?
Sure. So this is super interesting talk, by the way. Thank you for sharing this. I had a few questions about specifically how you use the CA. So you mentioned, there were a couple of things I wanted to clarify. One is you mentioned you have an offline CA, and then you mentioned that it's loaded into AWS private CA. How does this upload work, and like where does the CA running? Is it like on AWS directly, or is it replicated?
So sorry, I probably needed to include a diagram to make that a bit clearer. So the offline CA is completely offline. That is used to sign CSRs for intermediates that are loaded into ACM PCA. And then SPIRE server uses the PCAs as the upstream CA. So each of those intermediates in PCA has the name constraints on them for the trust domain.
Gotcha. So the offline CA is like the root.
Yes. So that's the one that's trusted across all of the trust domains. Yeah.
Gotcha. Then, sorry, a second question that I had is, what does the workload certificate issuance flow look like? Specifically, the RA capabilities. Does a private CA allow any workload to ask for any identity, or is there an RA in front of it?
So this in terms of the workload registration side of things, or
yeah, like let's say that I'm a workload running as a pod on Kubernetes somewhere, and I want a certificate. Do I talk directly to the private CA?
No. So that CA is used. So the offline CA is used to sign the intermediates for private certificate authority in AWS. That is only used as an upstream CA by SPIRE server. So SPIRE then issues the actual workload certificates through the SPIRE agent as normal. So we rely on the Kubernetes workload attester.
Great.
Mayor, one more. Jonathan, curious if you can talk about the trade-offs, your answer to Matt McFerrin's question on not using the standard X client forwarded client cert versus building your own. Just pass the SPIFFE ID.
That was merely I guess a choice partially made because I think at the time we were talking about what header to use. Envoy didn't actually have the ability to pass that header. And secondly, it was felt to be easier just to pass the SPIFFE ID in a header than have the services having to parse the forwarded client header.
Okay.
That makes sense. Matthew, comments you have there on the trade-offs, your thoughts? I know you looked at this for a while. I know folks at GitHub have also been looking at this.
And of course, we can pass both headers at the end of the day if we do find third-party software starts caring about the headers.
Makes a lot of sense.
Great.